Hi, my name is Joe, and I'm going to introduce basic machine learning concepts today. Machine learning is a set of algorithms that discovers patterns and symmetries in data. But the idea of finding patterns in data is not new. It dates all the way back to the Renaissance, when scientists were trying to find patterns in the physical world. Scientists like Kepler, Galileo, and Descartes managed to combine mathematical models with physical observations to make predictions about the natural world. I'm going to take you all the way back to 1581. Galileo was sitting in this cathedral in Pisa looking at the ceiling when he noticed this chandelier swinging because of the wind. As the wind was blowing, the chandelier was swinging at larger and larger amplitudes. But Galileo realized that measuring the period with his own pulse, he realized that the period did not change as a function of the amplitude. When he came back home, he tried it on pendulums with different amplitudes, and he realized that that's actually the case. This is one of the earliest sort of experiments where someone notices a pattern, does a more accurate experiment measuring data, and then comes up with a hypothesis, here realizing that the amplitude of the chandelier does not affect its period. But the more general problem we are faced with is finding models from data, finding patterns in data and finding models from data that can help us predict the future or predict data that we haven't seen yet. Now, speaking of science, it's interesting to look at early scientists that developed physical laws, empirical laws, where they would design an experiment and find some relationship between the variables in this experiment, the measurable quantities. So this started with Pascal's law that discovered the relationship between the pressure difference and the difference in height of a fluid in a tube. Hooke's law, Newton's law of viscosity, Ohm's law, Fourier's law, and Fick's law, all of these discovered relationship between some kind of flow quantity and a potential quantity. And they also, what's interesting that makes all these laws similar is that they're all linear. Empirical laws tended, at least then and still do, these are the foundations of science, they tend to be linear. And the art of discovering physical laws came down to designing an experiment where all the variables are controlled, everything is fixed and constant, except two quantities that can be measured. And by changing one quantity, scientists would measure the output quantity, the other quantity that's varying as a function of the input quantity. And in many of these cases, they discovered that they're linear, or in fact, the experiments were designed in a way such that these laws are, in fact, linear. Now you can ask about more complicated laws like the ideal gas law, and you can say this is sort of nonlinear, relating the pressure, the volume, the temperature, and the number of atoms in a gas. And you can say that this doesn't look very linear, it's a bit more complicated, but if you look at the history of where this law came from, you see that with Boyle, it started in 1662. He discovered that the volume and the pressure are inversely proportional by fixing the temperature and the number of atoms. And the same thing happened with Charles' law, Hamilton's law, and finally with Avogadro's law. So all these fixed everything else, varied only two quantities, and saw that they're proportional, and therefore that's your linear relationship. And finally, someone came in 1834 and unified all these linear laws into one general nonlinear law. So let's imagine ourselves to be scientists, Renaissance scientists. Let's say, Darcy came in the 1800s. Let's say we're Darcy, and we designed this experiment where we have a cylinder, and we put in porous material like sand in that cylinder. And we plug in a water pipe with a pump that pumps in water into the cylinder, and we can measure the flow rate Q that comes in and out of the cylinder. And we can also measure the input pressure and the output pressure of the cylinder. Now, Darcy discovered that there is a linear relationship between Q and the difference in pressure between the input and the output. And this proportionality constant is related to the cross-sectional area of the cylinder, the viscosity of the water, the fluid, and this is related to the properties of the fluid. K, which is related to the porosity and the properties of the sand, and the length of course, the length of the cylinder. What would Darcy have done if we're Darcy and we're trying to find this law? We would first design the experiment and then change Q and P in such a way that every time we change it, we record the data. So let's say we change Q, and then we record that P1 is 1.3, P2 is 1.0, and Q, the flow rate, is 22. Here I'm ignoring what the units are, but in reality, these are all units. They all have units. So Darcy would record all of these measurements, each one of these measurements, by varying these P1, P2, and Q. Now, P1, P2 could be the inputs, and Q could be the output. And the purpose of making all these measurements is that at some point, someone will come and say, hey, Darcy, I have an input pressure of 2.3, an output pressure of 1.4. What is the flow rate? And to answer this question, Darcy has to come up with a model. And that model, what it does is it takes in P1 and P2, and it maps it to Q. It's a function that maps P1 and P2 to Q. And Darcy discovered that that was the relationship. But on paper, he probably plotted these data points where he would put delta P on one axis. So he took the difference of P2 and P1, P2 minus P1, and that would be the difference in pressure, and plotted it against, plotted it with respect to Q. In fact, it's Q with respect to delta P, and got all these data points. So each one of these examples on the left in the table is just 1 point in this 2D plot. Now, what is this function f in this plot? Well, it's just a line that passes through these points. Now, Darcy's law is linear, therefore that's probably a line. It should be a line in that case. And it doesn't have a bias, so it's probably also passing through the origin. And in that case, it makes sense that a lot of scientists developed linear laws, because when it comes to doing things by hand, if you have variables that are related to each other linearly, your points will be on a line, and all you need is a ruler to just pass through all these points. The purpose of the evaluating model, of course, is to make predictions where I give you a new delta P, and now you can make a prediction. So I give you a query. I ask you what is given delta P, what is Q, and using the model, you can make that prediction. This is called a regression analysis to fit a model to data points, and this is a very common statistical method. And in this lecture, I'm going to focus on linear regression, which we will see in a bit. But regression is really a matter of fitting models to data. Now, going more towards the machine learning side, what machine learning scientists would call this table of data as, they would call it as training data, or your data set that you can use to fit your model. And each one of these entries is called an example. These are your measurements. Finally, you take this data and you try to discover a predictor from the data, and this is called the training procedure. And once you have the model, your inputs delta P F can be used to map your inputs delta P to your outputs Q. Q is sometimes called a label because in some cases it's a discrete, and in that case it would make sense to call it a label. And then there's something I did not mention in the previous slide, that Darcy in fact used delta P, the difference of P1 and P2, rather than the actual vector P1, P2 as input. And this is a very rudimentary form of feature extraction, where you're measuring certain quantities, but you don't use these quantities as they are in your model. you change them a bit. You change the variables. Here you calculate the difference. Maybe you can raise them to certain powers. You can apply certain functions to them. And this is something that you do as a scientist or someone who's building the model, is to extract the features. Now, this general framework, which applies both to physical modeling as it does to machine learning, poses a few questions. First, which predictors are possible? F can be linear, can be a line, can be a parabola. It can be something much more complicated. We can build a lot of complex functions nowadays. So what kind of functions are possible? How good is the predictor? This is something that we have to see based on the data. Given the data, how good is the predictor to make good predictions? And how can we find the best predictor? So these are questions we will address in this video. So let's change notation a bit to make things a bit simpler and clearer. So I'm going to assume that I have a one-dimensional input x and a one-dimensional output y to simplify things. But in the future, these could be any dimensions. My training set, or my data now, looks like this, where I have input-output pairs, x1 and y1, x2, y2, up to xn, yn. So I have n examples. A linear predictor would take an x, pass it through a feature vector, phi, and then my linear predictor would be f, and then finally I would get y as an output. I'm going to define my feature vector as phi x equals phi1x, phi2x up to phi kx. And here I have k features. Each one of these entries is a feature. And you can imagine that phi can be, for example, squaring x. It could be raising x to certain powers, or it could be even sine of x. It's some function of x that you choose. And then we'll define this linear predictor, which is fw equals w dot phi x. This is a dot product. And w is a fitting parameter. It's an unknown coefficient that we want to find to fit the data. And this, if we expand this dot product, this is nothing but a linear combination of the feature vectors. So a linear predictor is just a linear combination of the features. And the question is, what is the best linear combination that can give us good predictions? OK, so we define this linear predictor, w dot phi x. But maybe you're still a bit confused what this feature vector means. In the case of Darcy, we said it's just the difference of the p1 and p2. But what can we do with this feature vector? Now, I said first that let's say phi x is equal to x. And now your model would be f equals w times x. In that case, you would have a line, and it would pass through the origin, and w would be just the slope. Now, what if you want to have a bias, where you don't want the line to go through the slope? You want to shift it from the origin. You can simply do that by including 1 in your feature vector. So now this x will be the line with a certain slope. The coefficient of that will be the slope, and then 1 will be the bias. So your linear predictor looks something like this, where f of x is equal to w1 plus w1x plus w0. So you get a line that's off the origin. You can do the same with polynomials, where you define your feature vector to be 1x, x squared, x cubed. And now you get a model that is, you can have a parabola, a third order polynomial, as many powers as you want. But you can throw in really any function that you like. For example, if you know that your data oscillates, and you think that the sine function can capture that oscillation, you can include a sine in your feature vector, or cosine, or even an exponential, a tangent, or anything that you can think of. Your function doesn't even have to be linear. So you can, here I'm using indicator functions that are either 0 or 1 if the condition inside that bold one is satisfied. And this complicated looking feature vector really is looks like this, where it's just made of steps. So it's discontinuous. It's piecewise continuous, but it's still a linear predictor. So linear predictors can be very nonlinear in phi, and they can be very nonlinear in x. That's the whole point. Now, finally, there is something that not very common in machine learning, but becoming very common in modeling physical systems, is to define derivative features. Let's say you have inputs x and t, and out of the inputs x and t, you can calculate a numerical derivative. And this numerical derivative will look something like this, like delta x over delta t. And if you have these numerical derivatives as features, you can actually discover a differential equation. I'm not going to go into the details, but this is a very interesting direction for research that has recently been pioneered by Brunton, Proctor, and Kutz. The whole point of the slide is to tell you that linear predictors are not linear in x. They're, in fact, very powerful and very general functions. They're only linear in phi x and w. If you know the shape of your data, if you know that it oscillates at what frequency, if you know that it looks like a parabola or whatever it is, all you need to do is to include that sort of function in your feature vector, and then you can fit your data, you fit your model to your data accordingly. OK, so now we can define something a bit more general, which is the hypothesis class. Fw of x is a hypothesis, and it has unknown coefficients w. These coefficients w, we want to find the best set of coefficients w that would be our best predictor. We're going to call this best predictor Fw hat, which would have w hat as our optimal parameters. The hypothesis class is defined as Fw of x equals w phi x. This is our linear predictor, such that w is in Rk. W is a k-dimensional vector. And as you vary w, you can get different predictors. And the set of all these predictors with all the possible w's that you can have is called the hypothesis set. And as long as you're inside this hypothesis set, you can search for your best predictor. Now, there are, of course, predictors that are outside this hypothesis set that cannot be reached by a machine learning algorithm that finds the best predictor. The point of defining this hypothesis class is that once you choose phi based on your domain knowledge, you choose phi because you know that your data is oscillating, for example, so you choose phi to include sines and cosines, then your machine learning algorithm would be designed to find the best oscillating function within your hypothesis class. So your search is happening within the hypothesis class. To do so, to find the best hypothesis class, we have to first define the loss function. The loss function just measures how bad your predictor is. And that's why it's called loss. The higher it is, the more you lose, basically. And what it does is simply measure the distance between your prediction and the true value. So given x, you can make a prediction phi w of x. And you also know already y. And here, I'm assuming that I know the inputs and the outputs x and y. The distance between the prediction and the true value is shown here by this yellow arrow. And the larger this distance, the worse your predictor is for a single data point. Now, what is this distance? There are a few ways you can define this distance. One of the most common ones is to just compute the absolute value of the difference, and that would give you actually just the distance. And another is to calculate the square of the difference. The square loss is more common because it assumes a Gaussian distribution of the data around your model, and it has certain differentiation properties that makes it more common in practice. But you can imagine that you can define any loss you want that you want to minimize. If you think that there is something in your data that you want to minimize, you just include it in that loss as a function of your prediction and your true values, and then you try to minimize it. We want now to minimize the loss. But we don't want to minimize the loss for a single data point. We want to do it for all the points in our training set. So we calculate the average loss over all the data points. So we simply just sum the losses over each example xy, and then we divide by the total number of examples. And this would be our average loss, and it's called the training loss. The objective of a machine learning algorithm would be to minimize the training loss. So this is our objective: minimize the training loss and give me the best W that minimizes this training loss. Once we have this best W, W hat, we just replace it into the optimal predictor. And now our optimal predictor looks like this: FW hat equals W hat dot Vx. All right. How do we now do in practice? How do we perform this minimization? Our function ltrain, the training loss, looks like this. Our axes W1 and W2. Here I'm assuming that we just have two weights, W1 and W2. So the feature vector is two-dimensional. In practice, of course, this could be thousands or millions or even billions of dimensions. And the training loss function looks like this, like a parabola, where what we're looking for is to get to the minimum. And to get to the minimum, all you need to do is get the derivative of the training loss with respect to W, and find the minimum where the gradient becomes 0. In fact, for linear predictors, you can perform this operation analytically. It becomes a complex matrix multiplication problem. But we want to find this not analytically, we want to find it algorithmically, even if this loss function doesn't look parabolic. And this will be useful later for nonlinear predictors. To do that algorithmically, we basically want to start somewhere. We want to initialize our W1 and W2 somewhere random. We don't know what the optimal W1 and W2 are. And we want to take steps closer and closer to get to the minimum. And you can imagine that because the gradient is pointing in the direction of the steepest ascent, we want to go in that opposite direction, in the negative direction of the gradient of the training loss. And then we want to take steps closer and closer towards the minimum. An algorithm that actually does that is called a gradient descent. The gradient descent initializes W to anything. Here I'm just using zeros, and goes through iterations of updating W. And what it does is it takes W and it subtracts the gradient of the training loss. And then with each update, shown there by the arrows, you get closer and closer to the minimum. Now, how many times you perform this update? These are called epochs, capital T times. And how big is the step that you can take towards the minimum? This is called the step size. These two things you have to decide before you run your algorithm, and you have to tweak them yourself. These are called hyperparameters, which I will mention in a bit. Now, what is the gradient of the training loss? If we choose a square loss, then the gradient is given by that expression there. It's 2 times the prediction minus the true value times Vx. It's something you can also calculate analytically by hand. And in this case, this is what your training loss would be. You're summing over all training data, as we said earlier. Now, it turns out that the gradient descent algorithm is not very efficient because calculating the gradient over all the training loss is very expensive. And the reason it's expensive because in a lot of machine learning algorithms, you can have millions or billions of data points. And to calculate the gradient for each time step is very expensive. So it turns out it's more efficient to just calculate the gradient with only one example, with respect to only one example, rather than with respect to the whole data set. So we come up with something called the stochastic gradient descent. So the stochastic gradient descent does exactly the same thing, but instead of calculating the gradient with for all the data set, it calculates the gradient for only one example, xy, and it updates w based on that gradient alone. And you can imagine that will not take you in the steepest descent direction. It will take you in some general direction towards the minimum. Although it's going to take many more steps to get to the minimum, it's faster because calculating the gradient is faster. All right. So far, I've been talking about linear predictors, where fw of x is a linear function of w. And we talked also about feature selection, or this feature vector. How do we design it? The problem we want to address now is, what if our output is not a real number, but it's a binary number that goes from -1 to 1, or that is either -1 or 1. In fact, in reality, the output, discrete output, could be anything. I'll give you an example here, where in this case we have two inputs, x1 and x2, and the output y. Now the output can be either a green point or a yellow star. And the question now would be, if I give you a new x1 and x2 that's not in this table, what is the output for y? Plotting it on a 2D plot, we have these green points and yellow stars. And we want to somehow come up with a predictor that tells me, if I give you x1 and x2, is it going to be a green point or a yellow star? In practice, for example, one practical example that's commonly used in machine learning is, instead of using these 2 points, is cats and dogs. I give you an image, tell me if there is a cat in it or if there is a dog. So the cats and dogs would be the green point and the yellow stars. And the image would be made of pixels, and each of the pixels is given by one of x1 or x2. And of course, the image will have thousands of pixels, so you will have thousands of inputs. So instead of having here the vector of 2 inputs, you will have thousands of, like a thousands dimensional input. So also don't confuse this image with, or this 2-dimensional plot with earlier plot for x and y. Here, both x1 and x2 are inputs, and star and the points are outputs. Now we want to make the same. We have the same problem of finding f, our predictor. And in this case, w.phi(x) is in fact a line, a decision equals 0, in fact, is a decision boundary that separates the two classes, or the two categories. Now the interpretation of, if we just choose phi to be the identity function, or if we just choose phi(x) to be x, then w.x equals 0 will be the line. And if wx is positive, then it will be pointing, you will be on this side of the line. And if it's equal to something negative, you will be on the other side of the line. So in this case, the interpretation of w is simply the vector that's pointing in this direction, normal to the line. OK. Now, we can't work with green dots and yellow stars. So we define something more practical, which would be y equals -1 and 1. Now y can be -1, or it could be 1. And our prediction would be to either have a positive sign or a negative sign. So if w.phi(x) is positive, it's on this side of the line, and it's a green dot, then the sign will be positive. If w.phi(x) is negative, and it's on the other side of this decision boundary, then the sign will be negative. In this problem, we would define the L01 loss given by this function, where, again, it's an indicator function. So if fwx is different than y, then you have the wrong prediction. This will be 1. And that's bad, because you want your loss to be as small as possible. If fw is equal to y, then this is going to be 0, and this is good. Now we can, in this context, define confidence. How confident are we from our predictions? We can define the score, w.px. And as I said, when w.px is equal to 0, then you're on the line, and you're not confident at all. You actually don't know whether it's a -1 or 1 prediction. And as you get farther from the line, your score becomes larger, and you become more confident of your prediction. So the farther you are from the line, the more sure you are on that side. But of course, confidence doesn't mean that you're right. And this is why we define something called margin. And the margin will actually measure how right you are by multiplying the score by the prediction y. So if the score is positive, you're on that side, but the margin is negative, then it predicts to be on the true values on the other side. Then you have a negative margin, and this means that you're not correct. So a negative margin is being wrong, basically. A positive margin, on the other hand, means that your score and your true value are of the same sign, and therefore you're correct. So let's look now at the loss function as a function of this margin. In the case of a 0-1 loss, which we can rewrite as the condition of the score being smaller than 0, you can see that the loss is 1 for a negative margin, which we said if you're a negative margin, you're wrong. Therefore, your loss is 1. And if you have a positive margin, your loss is 0, which means that you're making a good prediction. So we have a loss. Let's take the loss and apply gradient descent to our data and then find the best model. But what's the problem with this loss? If we take the gradient with respect to the loss, you can see that no matter what the margin is, the loss is going to be, the gradient of the loss is going to be 0. It's always 0. The gradient is always 0. So how can you apply gradient descent? No matter what your margin is, no matter what your data point is, you're going to get a 0 loss, and therefore your weights are not going to update. So this doesn't work with gradient descent. There are models, there are algorithms that work with, there are algorithms where the 0-1 loss can work, but not gradient descent. So as a solution to that problem, we want to define a loss that at least has a derivative. So a first-order approximation would be to have a line, a linear function, that is more and more, the loss is larger and larger as your margin becomes more negative. And as the margin becomes positive, it becomes 0, because now you're more confident, so you don't want to penalize your model. And this will have only one derivative, which is -1. You can see also that this so-called hinge loss penalizes the model even if the margin is even a bit positive. It will push it to be more confident about its predictions until it's a bit more confident. So it will push it to be more confident. Now you might wonder, what about a loss function that keeps encouraging your model to be better? Why does it have to be 0 at some point? Well, before I get there, this hinge loss is actually used in predictors called support vector machines. Support vector machines are very common for classification, and they can be very efficient, especially with very high dimensional feature vectors. But of course, there's an extra term in the loss for support vector machines, which is a regularization term, and which I will mention in a bit. Now, going back to the idea of having a loss function that keeps penalizing, keeps encouraging my model to improve, this is where the logistic loss comes in. And the logistic loss is a smoother function that also becomes more negative with a negative margin. But you can see that even for positive margins, it is still positive, and it keeps the algorithm pushing itself to be more and more confident and correct, of course, about its predictions. And the logistic loss is used in logistic regression and is also very common for doing classification. Especially, it's used as a basis for neural networks, which we will cover next time. All right, so let's go back to the problem of finding phi, this feature vector phi. How do we choose phi? There's a big problem in choosing phi, and as you will see that once I give you data, let's say I give you some data about cars or some data, experimental data. You're measuring something in the lab, and you're trying to see if how the flow rate is related to the difference in pressure. You're whether you're a scientist or a computer scientist, you have data, and then you want to decide what this feature vector looks like. And this is one of the hardest tasks in machine learning. It sort of switches the problem of finding the model by hand to designing your feature vector. So let's go back to our simple problem of fitting some line through simple input-output data, x, y. Now, if I have this data and I'm trying to fit a line, let's say I just say I'm going to choose my feature vector to be phi equals 1x. You can see that the line does pretty well, but maybe something a bit more complex will do a better job. So you try to include an extra term, like a parabolic term, x squared, and you can see that it does pretty well. It does at least better than the x case or the linear case. And then finally, you say, well, it seems that as I increase more terms in my feature vector, I'm always doing better. So why not put in n powers of x, and maybe that will fit even better. And you can actually see that it does even better. It fits through all the points. But there is something fishy about the model. It seems that it's fitting too many points, at least. It's too complex. If I give you one extra point, well, in this case, you can imagine that if I give you one extra point that lies somewhere here, you will also do you will also do well when it comes to predictions. But in this case, if I give you an extra point, it seems that the trend of the data is going in this direction, not going down. But your polynomial is actually suggesting that the predictions outside this range is down. So it doesn't extrapolate well. It doesn't generalize well. This case is called overfitting, underfitting, where you have your model is too simple, and you have a high bias. There's a big difference between your model and your data. That's because your model is too simple. In the other extreme case, you're actually overfitting your data. You're fitting too much. You're not capturing the general trend anymore, but you're actually capturing the noise in the data. And this is a case of high variance. What you want is something in the middle, which is like this just right model. And this just right model will be the optimal trade-off between the high bias and the high variance case. This is called a variance bias trade-off, and it exists in all machine learning problems. And when you design your feature space, you always think about whether your model is a high variance model or a high bias model, and you adjust your feature vector accordingly. We can see the same problem from the point of view of this hypothesis class. In the hypothesis class, we can define the estimation error. The estimation error answers the question, how good is the predictor given the hypothesis class? So once we're in the hypothesis class, we know what the hypothesis is. How good is this predictor within this hypothesis class? So we can imagine that there is some optimal hypothesis in the hypothesis class called phi w bar. And what our algorithm found is phi w hat, because maybe we didn't run it for enough epochs, or our algorithm stopped short of getting there. Maybe our step size is too large. There could be many problems algorithmic problems to why we didn't find the optimal parameter or predictor in the hypothesis class. And the difference between FW hat and FW bar is called the estimation error. There's also the approximation error, where let's say there is some ideal optimal predictor of all time that exists out there in the world, and it's called F star. The difference between this best model that's outside the hypothesis class and FW hat, which is the best model in the hypothesis class, is called the approximation error. And the approximation error is really related to how complex your hypothesis is. So as you increase the complexity of your hypothesis, your function becomes more powerful, more versatile, and it can approximate F star better. So it can get to the ideal case better. But by increasing the hypothesis class, you make it less likely for you to find the optimal predictor, FW bar. So now, by increasing the size of the hypothesis class, you make your estimation harder. You make your estimation error larger. Instead, if you know, for example, that where F star will be where F star will be, so you shrink your hypothesis class and you try to make it as close as possible to F star. Of course, this is a somewhat abstract representation of what's happening, but it's always useful to think of overfitting, underfitting, the variance bias trade-off, and also how well your algorithms are fitting your model in this general framework. All right. At the heart of the variance bias trade-off is the problem of generalization. Because what we're interested in is to construct a model, fit this model, and then deploy it in the real world where it will make predictions of things that we haven't seen yet. But with the case of data, if we get the data and then we fit our model to the data, how can we know if it generalizes over unseen data? Well, we can sort of emulate that by splitting the data into a training set where we use to do our fitting, and a test set that we use to test what we have discovered. So you remove part of your data, you put it on the side, you run your training on the training set, and then you use that to test it on your test set. And if it does well on the test set, it means you generalize. If it doesn't do well, it means you're overfitting on the data. And this is how you prevent overfitting or even underfitting. In the case of underfitting, you're probably also going to do badly on your training set. But I think the biggest problem is to include too many features. And when you include too many features, you're going to do really well on the training set, but you're going to do really badly on your test set. You're not going to generalize well. Again, another concern that we have is that our feature space is too large, and therefore we're not going to be able to find the optimal solution. To fix that problem, we want to keep our predictor as low dimensional as possible, as long as we can make good predictions. So keep the dimension of W small. If it's d-dimensional, decrease that dimension to smaller, and that will prevent overfitting. So remove features that you think are not contributing to your predictions. And another more automated way to do that is to use automatic feature selection. One automated way is to add this L0 loss on W. It's the L0 norm of W. This is basically just automatically choosing the W's that are not making a difference on your prediction. And in fact, L0 is not something that you would use algorithmically. It just minimizes the number of non-zero elements as much as possible. A good approximation of this L0 norm of W is the L1 norm, the L1 loss. And this is an example of a regularization term. Another technique to keep your hypothesis class small is to keep W as small as possible, because as W increases, you also risk having a very high variance. So the way you do that, also algorithmically, is to add a term to your loss, which in this case will be an L2 norm. It's basically just the norm or the norm of W. All right. Now, there's something I skipped over in the L1 and L2 norm, is there was this lambda. And this lambda is called a regularization parameter. It's a regularization term. The question is, how much of that regularization do you want to add to your loss? You can add just a little or too much, maybe. If you want to make it very sparse, for example, you add, you make lambda large for the coefficients of the L1 norm of W. And on the other hand, basically, you have to choose this lambda. There are other things like the number of iterations and the step size. All of these are parameters that you have to choose, but that are not given beforehand. And also that you cannot optimize within your gradient descent algorithm because they're not part of the gradient of the training loss. But you can imagine that you can optimize over these parameters. The problem, though, if you do optimize over these, that now you might be overfitting over your test set, because what you do is you solve your gradient descent algorithm and you try with certain regularization parameter, number of iteration, and step size, and there are other such hyperparameters. And as you run this algorithm again and again and test it on your test set, you will also be overfitting over your test set. So you run that risk. So to overcome that problem, you split your data even more. And now you have a training set, a validation set, and a test set. You optimize your problem using the training set. And now instead of testing it on your test set, you test it on your validation set. Then you go back and you change your hyperparameters. Maybe you change also your feature vector. And then you run your training set, your training procedure again. Once you get the model, you test it on the validation set. And then you do that again and again. Once you know that this is the best model you can possibly have, you test it finally on your test set and to see if it generalizes well. Let's summarize this machine learning procedure and sort of summarize everything I talked about. Machine learning algorithm first starts with collecting data. And this is what you should always start with. You get data. You want to do a machine learning project. You're trying to solve a machine learning problem. You're trying to learn machine learning. First, look for the data. Once you have the data, you split it in three, as we said: training set, validation set, and test set. Before you do any machine learning, first look at the data. How does it look like? You can really use a lot of domain knowledge, depending on what the data looks like, what the data refers to. You might know that, for example, certain variables are related in certain ways. In physics, for example, you know that mass, energy, and momentum are always conserved. So you have certain constraints on the data. And you can see that in the data when you plot it. And of course, understanding the data before you do any machine learning will help a lot in designing your feature vector. So once you visualize the data and you understand how it looks like, you design your feature vector. Phi x equals some 1x squared. Could be a polynomial. We talked about that. You design your feature vector. Now you change your hyperparameters, t, eta, lambda, which we talked about. And then you run your machine learning procedure, your gradient descent, to get to the optimal W1 and W2. Once you get your optimal predictor, you try it, you test it on your validation set. And most probably, you're not going to like it. Well, you're going to want a better model. So you're not satisfied. You go back and look at the data. Why didn't you do well? What are the problems? Why is it not predicting well? Is it overfitting or underfitting? Is it a high variance or high bias model? So what you do is you redesign your feature vector, your feature extractor, and you run this whole procedure again. Of course, you can sort of automate all this procedure where maybe you have some hypotheses in mind. So you put these in a loop. just try these hypotheses. Of course, also you can do some hyperparameter optimization, where in every step of this loop you change t, eta, and lambda, and you'll see in neural networks there are more of these hyperparameters. And then you run your algorithm, and then you come back and test your test set. And you can do this loop thousands of times if you want, but always use the validation set. Because once you're done and you think that you found a good model, you take that model and you test it on your test set. And you get the loss of the test. And this will tell you if you're generalizing well. This is very possible. It's most likely that you do well on the training set and well on the validation set, but not as well on the test set. And that's why you want to test the generalization power of your model using the test set. So this is going to be everything for today. And a lot of these concepts that I introduced today will be very useful for neural networks or for any machine learning algorithm. Please let me know if you have any questions. I'll put my email and references below. Thank you.